get that so we will convene here, and if it doesn't work out for it, we'll roll on over the long call. And I'll put this on Zoom, assuming that CCID keeps everything working. But be there. I mean, it'll be the place to be, social mecca of the Western world on Saturday. I anticipate that, like, you know, y'all are grad students, you probably don't need much of a review. So this will be kind of a good chance to sort of catch our breath. You know, kind of see where we're at. There's points of confusion that I can work out. And we obviously we'll talk about that. Any questions that you may have on the exam? Okay, so questions before we get going? So the last time we were talking about rings, and I give you theorem 512, which I won't repeat, but I think you should work out most of these things kind of for yourself as an exercise, but I'll give you kind of a theme of it, right? Like one of the things is that right, here's why this kind of thing is true. Truth here. What happens if you add 0 times a, whatever that element of the ring may be? What happens if you add it to itself? Well, I can use the distributive property to do that. But 0 equals 0 is 0. So I get 0a equals 0a and 0a. Now you're talking about an abelian group, right? You have x plus x is x, right? So, right, so it's just cancel one of these, right? And of course, I think that this makes it obvious how to do it when A is on the other side as well, right? Another one was, yeah, it was too. How would you do something like this? Well, so the way I would do this is, this one would be a complete proof, just do one bit of it. If you look at minus AB, well, I'm sorry, that. Right? What happens if you have this? This is I can suck that B out of this side. And that's 0 times B, which is 0 by part 1. Right? And so what does this mean? This means that minus A, B, plus AB is 0, which is equivalent to saying that minus A times B minus AB, which is this part. Now do it from the other side of this part. So that's the way these kind of things work out. And it's silly, but you want to be able to do this. I had a friend one time that asked me, and this was a friend of mine who was, you know, a smart enough fellow, but he was like, now, can you tell me why it is that the product of two negative numbers is negative, right? And it's all this kind of thing right here. Or two negatives is positive. Right? Maybe I hope I didn't have to correct them. Definition. An element A and R is said to be a left respectively. Right. By the way, there's going to be a lot of these respectively kind of things going on. Because rings aren't necessarily created. Zero divisor. If there exists a non-zero, has to be a non-zero, B and R such that AB equals 0. Yeah. If A is a left and a right zero divisor, it is a zero. Okay, so when I say zero divisor, I mean it's a left and a right zero divisor. Let me give you a word of caution. This B and this B do not have to be the same. Right? What it means to be a left zero divisor is I can hit a non-zero element on the left with this thing and get 0. What it means to be a right zero divisor is I can hit this thing, I can hit a non-zero B on the right with this thing, right? If it's a zero divisor, that doesn't mean that you can use the same B from the left and the right. What it means to be a zero divisor is there's a non-zero B such that AB equals 0 and a non-zero C such that CA equals 0. It could be different. And let me up the voltage. Just one more thing in this definition. If A n 0, n greater than or equal 1, then A is no potent. Let me point out here that if you have a ring that is not 0, the 0 ring, you've always got the ring that's 0 because it's only in 0. That ring's a little bit pathological. But if you have a non-zero ring, that is, it's got at least one element that's not 0 in it, 0 is always a zero divisor. Because just take that non-zero element times 0 and you get 0. There are some people that say that 0 is not a zero divisor. We call these folks incorrect. There are mathematical reasons why zero divisor should be zero divisor. And certainly, any nilpotent, 0 is an example of a nilpotent. Here's kind of a similar, this is sort of the antithesis. An element of a ring with identity, here I'm going to assume that you don't need to zero divisor. But are the an element that's said to be left right convertible. If there's an element B such that BA is 1. If such a B exists, then it's called the left, but right inverse, right? If A is both left and right, convertible, all or sometimes an invertible element. So, and I'll use this notation. Sometimes if I say U of R, this is the collection of units of R. These are the elements that are both left and right invertible. Notice implicit in this notation is that R must be a ring of identity, right? Because it doesn't make any sense to talk about units if you don't have something to invert them to, right? Let me point out the units of R is in fact a group, right? So this is actually a multiplicative group that is contained inside the non-zero elements. Here's an example. Look and see. Oh, what's the 36. Can anybody identify the units in this? Yeah. Was it which one? That's right. I mean, if you just forget about the halves here and look at the numbers that are relatively prime to 36, then I'll list them all. Well, here we go. 1, 2, 3, 4, 5, 7, 11, 13, 17, 19, 23, 31, 35. Yes. So that should be the exhaustive list of everything. So, you know what the zero classes are? It's everything left over, Mike. Zero, 2, 4. This one, 2, 3. Actually, it should be all multiples 2 and all multiples 3. Okay. 12, 14, 15, 18, 20, 30, 32, 33, 34. I guess it should be 24 at least. This is a good day for me. Anybody identify the null tokens? Oh, let me get you rolling, shall I? Well, 0, that's always going to be 1. Are there others? 5, 36. Yeah, but all these are 36. Right. And if you look at 2, you the powers of 2, there's 2, 4, 8, 16, 32.
My brain is thinking accurately that instead of like because we've been in groups, so I was thinking 2.
Sure.
That's the powers.
Well, let me ask you, so what do we got to do now, right? To be a nilpotent, that means that a high power of that has to be divisible by 36, right? When I take a big enough power, to be a nilpotent, big enough power of this has to be 0. Translation, the big power of this has to be a multiple of 36. What do you need to happen for an integer to have a big enough power of it to be a multiple of 36? All you need is 2 and a 3 in it, right? Everybody agree? And that's certainly necessary, right? Because if you don't have, if you're missing any prime factors, you're never going to, you can't get the prime factor out of that. And if you have a 2 and a 3, then actually, if you have a 2 and a 3, really all you got to do is square it, right? So, what do we got? Oh. So it should be 6, 12, 18, 24, 30, 36 nilpotents. And everything's divisible by 6. Of course, this is an easy example because this is a finite ring and it's commutative and it's got identity, so there's nothing really strange happening, right? You might look at matrices. Can anybody think of the nilpotent matrix? It's not a 0 matrix. Okay, that's right. Any upper triangular matrix sort of marks 0. Fine. Move 5 by 5 matrix. And by the triangle, I should say strictly of the triangle. And actually, it doesn't really matter. I can put anything I want up in these 6 entries here that are above the 1s. When I square this, the marches the 1s here. And when I cube it, the marches there. 4th power, 5th power. 8 and the 5th. Let me also give you kind of another dangerous bend here. Let's look at another example. Let me contrast finite rings here. I don't want you all to get the wrong impression by this example, although I do like to see 36 example. Because it gives the impression that in a ring, you've got 2 things. You're either a unit or you're a 0 divisor. This is wildly untrue. What are the units of the ordinary integers? So ask yourself this. Right. Which integers have reciprocals that are still integers? Well, that's it, baby, right? I use this to denote the zero divisors and the nilpotents, it's only zero. Do I agree with it? I mean, if you have in the integers, if you have something times something at zero, one of those two things has to be zero. So the only zero divisor is zero itself. So what this means, of course, the integers is most elements are neither units nor are they zero divisors. In fact, everything that's not zero plus or minus one is an element that is neither a unit nor is it a zero divisor. Okay. One. And, left inverse. B and right inverse. C. Yeah. B. So this is actually, as a consequence of this, this shows that inverses are unique as well. C is 1 times C, which is BA times C, because B is a left inverse, which is B times AC, B times 1. And so left inverse is right inverse are the same, and they're all unique. Yes?
How are they superior?
Right, and B is called the left inverse.
Oh, right.
Okay. So more definitions as we sort of plowing through new territory here. Definition 5.6. Non-zero ring. And there's a logical technical reason why I say non-zero ring. And some people sometimes, people like me that like to work with rings identity, oftentimes you'll see in papers will say, let R be a ring with 1 equals not 0. Right? The reason for this is if you have a ring that's only 0, you can interpret 0 as a multiplicative identity, right? Because 0 times anything is because there's only 0 there, right? It's pathological, so I'm going to throw out the 0 ring, which is a very silly ring. With identity is called and with identity, since I said it's a non-zero ring, this prevents me from saying the identity is not 0. It's called integral ring. It's technically called an integral domain, but if you ever see me just say, let R be a domain, that means integral domain. sometimes the word integral is left off. If R has no non-zero zero divisor. Now, remember, an integral domain must contain a multiplicative identity. This is part of the definition, and this is often overlooked. Don't forget that. This means integral domains are the nicest. They have identity. And you get this equation that you use, you get to assume the thing that you usually assumed in high school. I can remember that back in the day when they would like try to get you to solve equations, and you'd always factor something, and this times this is zero. What can you assume? That one of those two things is zero, right? That's the cool thing about integral domains, is they allow you to do what you did in high school. It's the easiest kind of thing. If the product of two things is zero, one of the things is zero. So integral domain got identity, and it's got that property. Now, let me point out that if you look at the even integers, that is a commutative ring, right? And you've still got this property that A times B equals B. It doesn't matter. If you multiply two even integers, you get zero. One of those two integers has to be zero, right? But it is technically not an integral domain because it doesn't have an identity. To add to this, a ring, not necessarily commutative, D with identity is a division ring. If the units D minus C. So that is to say, it's a division ring, and I think that's kind of that's a very kind of good name for it, because what it means is you can divide by anything that's not zero, right? Because anything that is not zero is a unit, so you can put it in a denominator, so to speak. And finally, a field is a commutative division. Everybody? So you got integral domains, right? That just means that A times B equals zero, means one of A and B is zero, and it's got an identity. You got a division ring, it means that every non-zero element is convertible. And we got a field, which is division ring is field. So let's start building on the theory of this. Here is the division ring. Then C has no non-zero zero. So a field and integral. So if you have a division ring, there aren't going to be any non-zero zero values. If A not 0, then variance is x and b such that x of 1. Therefore, x a and b, x a and b 0. So that proves it. So that's a times b equals 0. If a is not 0, then b must be 0. Any questions? You may, I'm going to run a couple of examples by you. Anybody it feels very important. Right. What's the smallest infinite field you know? Any others? You can actually build fields out of almost anything. This is rational functions. So this is rational functions in one variable of a complex number. So this is a quotient of two polynomials. Top and bottom are just polynomials with polynomials in variable x, complex coefficients, and the denominator is not 0. And you can tag on sometimes with many variables. You can go bananas. There are finite fields. There are fields, these are all of order p. And actually, it's once again back to the integers. It's including algorithm basically that gives these Z mod is a field. Z mod n is a field if and only if n is non-zero prime. So these are all, so you've got fields of order p for any prime p. And in fact, you've got fields of order p n for any n. They are not Z mod p n. They're finite extensions of this. And if you're interested in 852, we'll talk about that. They're also infinite. So in this field, it's kind of interesting because if you take any element of this field and you add it to itself 2 times, you get 0, right? It's this will say characters. If you add anything to itself 2 times, you get 0. They're actually infinite fields of characters. And that's really more of an 852 thing. Here's another example. Here's a way to construct rings that are just full of zero divisors. Take any family of rings, and in fact, you could take each Ri to be the integers, right? You could take infinitely many copies of the integers or whatever you want. Construct 2 rings. you know exactly what these two things are from the group theory point of view, right? This is just entries. These are nets. Ri, I, and gamma. So it's Ri equals 0 almost everywhere. And again, the almost everywhere means for all but finitely many of the entries. And this is nets. With no restriction. This is what these things are as a billion groups. So the only thing I've got to do, I think, to convince you all that you can make this into a ring is tell you how to multiply. And so, in either one of these, when I multiply two of these nets, I got to get a new net. What's and he's supposed to multiply? Yeah, that's right. Just coordinate wise. This makes both the direct sum and the direct product new rings. And these rings are actually isomorphic if your index set is finite. But as a general rule, these things are just chock full of zero divisors in the following sense. So for example, if the index set is bigger than 1, then non-trivial zero. Because, for example, if you look at three copies of that, well, actually, let's take 2 copies. Let's show you. Actually, and I'll do it. I'll assume that all the rings are not the 0 range, because otherwise, apologies again. But for example, if these are not the 0 ring, just take a non-zero element of R1 and non-zero element of R2 and look at A comma 0 times 0 comma B. This is the 0 element. And there you go. And notice neither one of these are 0. Okay. Let me point out also that if this is so in other words, I don't have a great hope of ever building an integral domain display. The only way that I can build an integral domain display is if your index set is 1 of size 1. And then why are you even talking about direct sums of direct product? If each Ri has identity, so the direct product Ri because the identity there is just taking the 1 in every coordinate, right? And direct sum of Ri if and only if the index sum is finite. So the direct sum of rings, if you've got an infinite direct sum, then you don't expect to have an identity. Okay. Any questions so far? Okay, here's one of my favorite ones. I've got this listed in the notes. It's 519. I'm going to rip it off as a corollary. I'm going to put something a little bit more general. I don't like it so much. So my situation here is, suppose that you have a finite ring. Elements of R. This reflects what we did in that example with the Z36, where it turned out every element was in the unit of zero value. This theorem generalizes this. Any finite ring, you've got this problem. So let's prove it. I guess you could say that I don't know. I don't want to get an argument with this here, but we'll say zero ring. We'll throw the zero ring out. We'll say it's vacuous and true. So let A. Let's take any non-zero element. Right. Notice if A, if R is not the zero ring, then any non-zero element, then if R is a non-zero ring and zero, it's certainly zero divided. So that's taken care of, right? So what happens to a non-zero element? I need to show that a non-zero element is either a unit or zero divided. Consider by the way, there's something interesting that you notice, because notice I claim I want to prove that everything's a unit or a zero divisor without assuming that R has an identity. I never assume that R has an identity. I'm going to use that for free, which is kind of interesting. Consider the set of all powers. Right. Now, this, of course, is a subset of R. So, this infinite list has repetition. Right? That is to say, this is an infinite list, but these lists are all elements of a finite ring, and so they can't all be distinct. So there exists n bigger than m such that a n. Everybody okay with that? Got to repeat some point or another. Now, I'm not going to. Oh, it's tempting to now write a to the n minus m equals 1, right? By dividing out here. But I can't really do that because I don't know I've got a 1. Am I agree with that? That's a little problematic. But I will notice this. Oh, and here, let's suppose A is not. Because if it is, I'm done, right? Because I'm claiming everything zero divided per unit. Now let's see what I can do here. pull this out here. I want to pull it out. There we go. There we go. Now that I can do. Since A to the M, say it's not a zero factor. It's pretty easy to show this inductively, right? Let me justify that a little bit. Let me justify that statement. Suppose A is not a zero divisor, but now suppose A squared B is a zero divisor. That means A squared, or suppose A squared plus B is zero, that means A times AB is zero. Right? But A is not a zero divisor, so that means AB is a zero divisor. Or that means A times B is zero. That's where so this is how you reduce things, right? And so, what we have here, we have the product of these two things is zero, and A to the n minus 1 is not a zero divisor. So, what does that give me? That gives me that A to the, whatever that mass is, n minus n plus 1, 0, and therefore, so I'm going to make a quick claim. I claim A to the n minus m is R. I claim that this function is like an identity. Right? Notice that A to the n minus m makes sense because n is bigger than m. Then that is a positive power. N minus m is a positive power of A, so it's an element of the ring. Makes sense. I claim this is the identity proof. Using this equation right here, let's multiply A to the n minus 1, n minus n plus 1 B, AB. This is A to the n minus m plus 1 minus A B 0. Well, actually, A to the n minus m plus 1 B minus A B 0. Now I want to factor an A out. This is A to the n minus m B minus B 0. Again, A is not a zero divisor. A to n minus m B minus B 0. So what we've shown is for all B and R, A to n minus mb equals B. Similarly, B becomes A to n minus m n minus m. So, well, that proves that it's not a zero divisor. It has to be. Any questions? So I'll give you a corollary. See it all over the place. 5, 9, B. 5. What does it mean to be a finite integral domain? It means it's got a 1 in it. So it's not the zero ring. It's an integral domain. So there are no non-zero zero divisors. So that means that all non-zero elements are a unit. And it's commutable. Any finite integral domain. Okay, any questions? Any questions? How about y'all out there? Any questions? Okay. Well, you all take care, and we will see you by Friday.